Welcome to Chapter 4. We'll be talking about alkanes. Now, the compound here is not shown. The relationship between these compounds. So this is this compound and this compound. Now, for this chapter, the Pogel exercises, Pogel 4 and Pogel 5a and Pogel 5b will be very helpful. Those Pogel activities. Also, one of your goals here will be to determine the relationship between compounds. So you'll learn from Pogel 4 that and you also name these alkanes. You'll want to first always do the molecular formulas, and see if they are the same. If they are the same, then they're going to be related. And then we'll have to figure out how they're related. So here we have 6, 7, 8 carbons. And then hydrogens, we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You might want to count that again. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Here, how many carbons we have? 1, 2, 3, 4, 5, 6, 7, 8. And then how many hydrogens we have? 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So they have the same molecular formula, so they are related. If they had different molecular formulas, they would not be related. They have different connectivity. And what I like to do is I actually like to name these. And then you would know that they're not the same molecule. You will learn how to name this. This would be 1, 2, 3, 4, 5, 6. You're going to learn that this is 1, 2, dimethyl cyclohexane. And so since there's 6 carbons, that's hex. These are alkanes, so that's ane. And they're cyclo because it's in a ring. And then you notice that the substituents are what's coming off of the main chain. So in this case, the main chain is the cyclohexyl. And so substituents would be these. And you'll find that they're 1 carbon, so they're methyl. And that's a YL for a substituent. And since there's 2, there's di. And then they're coming off of carbons 1 and 2. So 1, 2, dimethyl cyclohexane. You have dashes between numbers and letters, and you have commas between numbers. The name of this compound, then, you find the longest chain, and you'd need to include that double bond. 1, 2, 3, 4, 5. 5 is pentane, pent, but it's not an ane, it's pent on the carbon 2, 2-ene. That's a functional group. And then you have your substituents, which are this, this, and this. And so this would be 2, 3, 4 trimethyl pent-2-ene. And then you'll learn that and learning how to name alkenes will be different than this chapter. This chapter you'll learn how to name alkanes. Where you can see they have different names. They're different compounds. They're constitutional isomers. They have the same molecular formula, but they have different connectivity. And different connectivity would give them a different name. All right, so this is chapter 4, and some of our learning objectives for chapter 4 is I can name alkanes. I can draw the most stable disubstituted cycloalkanes. I can convert Newman projections. We'll talk about a Newman projections to name, structure, and back and forth. And then, and these are also the most stable. So we have a few learning objections regarding Newman projections. All right, so this is undecaying. That means there's 11 carbons. You see it's kind of like the Charlie Brown zigzag. The reason why it's a zigzag is because these have free rotation, so they can rotate around this single bond. And you'll find that in these are called acyclic alkanes because they're a straight chain. They want to be in a staggered Newman projection. And so the Newman projections are really helpful for, I think that's POGIL 5A. So you'll know about Newman projections. Newman projections are like when your eyeball is looking at this carbon and how it sees that carbon. And just know that the zigzag line skeleton structure represents the most stable Newman projection. Okay, cycloalkanes, they actually have carbons joined in one or more rings. And so you would write cyclohexane because there's 6 rings there. And you see, you're also going to learn that the conformation for the most stable conformation is, I'm sitting right now, okay? When I get done, I will stand. If you want to, right now, you can touch your toes, okay? Now, while you're sitting or standing or touching your toes, you're still you. You are still you. You're just in a different conformation. We're going to learn another word later on. It's called configuration. And these are different compounds. They're actually different. So you're going to learn different relationships with these compounds. You've already learned that if they have the same molecular formula, but different connectivity, they are constitutional isomers. And you've been doing that a little bit with POGIL 1 and then POGIL 4. So these are actually different compounds, but here, conformation, this is a 2-dimensional drawing, but really, the cyclohexane is a chair. Okay, so each one of these hydrogens here, you'll see are axial. See if you can see that that's axial. Axial is perpendicular with the plane. Okay, so you're going to learn to draw these. This is the hydrogens are perpendicular with the plane and they all go up. And then you have these equatorial hydrogens. And this is how they're drawn here. And you'll practice drawing these, okay? So this is a conformation. So even though it's drawn in this 2-dimensional form, this tries to capture the 3D form. So it's like the difference of when you draw your TV box and then you learn how to draw more of a 3-dimensional box. I mean, which one gives a better representation of that if that was your television screen? The 3-dimensional. So you do have a tetrahedral carbon. Each one of these carbons is an sp3 ethane. So you need to start learning this. Methane is 1 carbon. Ethane is 2 carbons. These are sp3 carbon here. And you know sp3 is tetrahedral, 109.5 degrees. So drawing propane, this has a hydrogen coming at you and going back, hydrogen coming at you and going back. And so we're going to like to draw the line structure and there are 3 carbons there. That is propane. Pentane. Pentane can be drawn all kinds of wacky ways, okay? You'll see these are all the same because they can rotate around these single bonds, okay? They can rotate and they can, while they're rotating constantly at room temperature, they can be in all of these, and these are all the same. There's nothing different here. You might draw them differently, but they're all the same. And that's pentane with 5 carbons. Now, constitutional isomers, they have same molecular formula, different connectivity. These are constitutional. They're also called structural isomers. I'll probably call them constitutional isomers, and they're going to have they're different compounds. They're going to have different melting points, different boiling points. Okay, so this is butane. 1, 2, 3, 4. There's butane. And you can get you some molecular model kits for like $20 if you would like to make some models, and you can use those for your exams. Might be helpful. Okay, so here's this carbon here, and then you have 1, 2, 3, 4, and they're named differently. So this one you'd find the longest chain for the naming, and you have to go all the way from one end to the next, and that's butane. There's no substituents off of that. This one, the longest chain, would be 3, so there's propane, and then on carbon number 2 you have a substituent, so 2-methylpropane. And see, the name is different than butane. They both have a molecular formula of 4 carbons, 3, 6, 7, 8, 9, 10 hydrogens, 4 carbons, 3, 6, 9, 10 hydrogens. So these are constitutional isomers. You need to know up to 10. Okay, so there's 10 carbons. So methane is 1, ethane, propane, butane, pentane, hexane, heptane, octane, 8. And we got one more there. Nonane, you get it in 10 decane. Okay, the cycloalkanes. So you have cyclopropane, which would be 3. And this is going to be a very strained ring. Okay, so when you have this is an sp3 carbon. So an sp3 carbon, what's the bond angles? 109.5 degrees, right? That's a bond angle for an sp3 carbon. However, what is the bond angle here? Do your geometry, folks. Yeah, it's 60 degrees, isn't it? Do you see the deviation between 60 and 109? So this has a lot of angle strain. Angle strain. That's hard. Try to make that in your model and you'll see. Cyclobutane, 4 carbons. This also has angle strain. And we're going to learn different conformations to relieve angle strain. And once again, this is an sp3 carbon. So that's 109.5. But this is 90 degrees. 90 degrees is less than 109.5. Cyclopentane. Now you're getting, this is called an envelope. It will adopt a conformation such as this. 1, 2, 3, 4, 5. It's called the envelope. We'll see future slides. The envelope relieves this angle strain. So the conformation is, and we've already talked about cyclohexane is actually a chair conformation. It's like a little lounge chair, okay, to relieve the angle strain. Okay, so the nomenclature. I always go with the longest chain. You can go forward or you can go backwards. So but you got to go from one end to the next. It's like and it's all the carbon. It's the carbon, like the choo-choo train. The functional group will determine if it's an aldehyde, that'll be like al. If it's an alcohol, it's an OL. If it's an alkene, if it's an alkane, which is single bonds. If it's an alkyne, so the suffix here is based on the functional group, and the prefix are the substituents. And we have to number them, and we have to give them a name. So the first thing you want to do is find the longest chain. They're just showing you the substituents. Methane, if it's a substituent, it gets the YL. That's methyl. Ethane becomes ethyl. Also, your book, your POGIL exercise 4 has a list of common names you need to know for substituents. So we won't spend a lot of time here because you do have the POGIL. So here, they're just showing you that if it's a substituent to the parent name, then that's propyl, isopropyl. So there's propyl, 1, 2, 3, and this is your chain. There's isopropyl, it makes a Y. You see? 1, 2, 3, and it makes a Y. That's isopropyl. And then you have the butyl. So this is butyl with 4. And then you have isobutyl. You see, there's your Y. Sec-butyl. It comes off the second carbon of the butyl. So that's sec-butyl. And then tert-butyl makes a cross. 1, 2, 3, 4. So you'll notice that they're all butyl because they have 4 carbons on the substituent. These are the ones you need to know. And you, like I said, you have a POGIL. Okay, the first thing you want to do is find the longest chain from, and this is a fun exercise, so just kind of have fun with it. 1, 2, 3, 4, 5, 6, 7, 8, or you could take your time and check this. 1, 2, 3, 4, 5, 6, 7. And I just go through all of them and see. And then, like I said, it doesn't matter. But the one thing that does matter is you got to go from one end to the other end, whether it be going left to right or right to left. Now, when it does matter is when you have different substituent groups. And you want to give the lowest number of substituents. So here, this has more substituents, and you got 1, 2, 3, 4, 5, 6, 7. So 7 is heptane. These are all single bonds. And then here you have, then you got to count 1, 2, 3, 4, 5, 6, 7. You have a 2-methyl, and then you have a 3-ethyl. And so then you're going to put those together. Okay, so what is the parent name for this compound? One, 2, 3, 4, 5, 6, 7, 8. Hopefully you got octane. Here, they're trying to decide, do you count from left to right? Or do you go right, see the number 1, to left? So once you find the longest chain and you figure out, okay, we have 8, that's octane. Are we going to number from left to right or right to left? And the correct way is to give the first substituent the lowest number. So this gives it a 2. It's really the set of substituents. And the first substituent here is a 3. So we're gonna do left to right. And so then this would be 2, that's a methyl, and that's a methyl. So 2, 6 dimethyl. And then this is an ethyl, 5-ethyl. and then you'll put these together. Um, if they're the same, so you have a tie. They're both on a 2 here. So which one do you go with? Well, this one gives us a lower set of numbers, 2, 3, 5. This is 2, 4, 5. So you see the 3, the second one would have a lower number, so this would be the, once again, go left to right. The earlier letter gets the lower number. Okay, so in this case, they're just showing you alphabetical. E comes before M in the alphabet. My goal is if I can draw the structure from your name and vice versa, then we're usually pretty good. Now, your substituents, they get a number and a name. So here we have a methyl at 2, a methyl at C6, and an ethyl at 5. When you have more than one of the same, then you've got to combine them. So 1-6, and that's a dimethyl. And when you combine it, you use a prefix. And that's what they're talking about. Prefixes. Usually all you need, di or tri or tetra. You rarely get more than tetra. And this would just be ethyl. And when there's just one, you don't do mono or anything. That's just 5-ethyl. And so here, and you would put, you're going to add them all together to make one name here. And so you see here, and why did the 5 come first? Because ethyl, E comes before M in the alphabet. So you probably have some online homework questions too that will help with this concept of naming. Okay, and then you kind of combine them all together. This is octane, so it's just an alkane, and we have 2, 6 dimethyl, and we have 5-ethyl. And they're just showing you that it's a single word with no spaces, and you use commas between numbers, and you use hyphens between numbers and letters. All right, so now your turn. See if you can name this compound. So I think we already established this is octane. So here we have octane on all of these. Now are we going to number them from left to right or right to left? Well, if we go right to left, 1, 2, 3. Here we go 1, 2, 3. So that's 3. But then if we go 1, 2, 3, the next substituent is 5. If we go from left to right, 1, 2, 3, the next substituent is 4. So we'll go left to right. 2, 3, 4, 5, 6, 7, 8. And then what are our substituents? You have a 3-methyl, a 4-methyl, and a 6-ethyl. Now, if I tell you I live on Woodbine Road in Lexington, well, that might be helpful, right? But if I don't give you a house number, you don't know what house I live on. Well, just like this substituent, you need to give a number of what carbon these substituents come off of. That's why you have the 3 and the 4, and you combine these two to be 3, 4 dimethyl. And here we have 6-ethyl. Ethyl becomes before dimethyl because the M versus the E. We don't look at the D. And then what was this octane? And there we see that that is the answer, D. Okay, if you do cyclo, then you find the parent cycloalkane. So there's 6 in that cyclohexane. And then when you count, you can either go clockwise or counterclockwise. So you want to start with, make one of these number 1, because you got to, and you got to get the lowest number combination. So this would be 3 if you go clockwise, and if you go counterclockwise, and this is number 1, that would be 5. So you're going to want to go clockwise, right? Because the 1 and 3 are lower numbers. And that's what they're showing you here. So this is a 1 and 3. So this would be 1, 3 dimethyl cyclohexane. Here, they're showing you those counterclockwise there wouldn't work. This is a methyl. This is a tert-butyl group. So here you have an ethyl at C1 and a methyl at C3. So you would make the ethyl 1 because E is the earlier letter in the alphabet. Now, when do you name it as a substituent versus the chain? So this is 6 carbons in the chain, so then that would be a cyclobutyl group as a substituent. This, because there's 4 groups, that would be a butyl, and that would be cyclohexane. So here's just some examples that you can look at. Now, we won't be looking at these. These are just common names of polycyclic molecules. If you end up doing some polycyclic research, then this might be important to you. They're just showing you some applications of alkanes, so fossil fuels, natural gas, methane. You also have propane gas. You've probably heard of propane gas. Petroleum is a complex mixture of compounds made of hydrocarbons, 1 to 40 carbons. This is how we get the crude oil. Gasoline. There's some images you can refer in your book for these structures. Plus you have your PowerPoints in your course documents. Okay, so alkanes, this is intermolecular forces we kind of talked about. They're nonpolar, so anything which is carbon hydrogens are nonpolar. They exhibit weak van der Waals forces, so they're going to have low boiling points and low melting points, and their solubility is going to be in nonpolar solvents. So it's kind of like gasoline, right? Gasoline is octane. So 1, 2, 3, 4, 5, 6, 7, 8. And you know that oil and water are going to make 2 different layers, okay, because they're insoluble in water. Alkanes are going to be soluble in organic solvents. So if you take gasoline and you have something like benzene, which is an aromatic hydrocarbon, that's going to be found in the oil layer, and you would not find it in the water layer. They have low boiling points and low melting points compared to polar compounds with their similar size. So, but if you're just looking at van der Waals and you're comparing like 3 compounds that all do van der Waals, then you increase the number of carbons, and that's going to increase your boiling points, or it'll increase your melting points because you do increase the surface area on that. So looking at this is butane. And these are just van der Waals because there's no other functional groups. Boiling point 0 degrees Celsius. But you increase the carbon now, 1, 2, 3, 4, 5, 6. This is hexane. And you see that the boiling point went up 69 degrees. But this is still van der Waals because they're alkanes. Now you put in an alcohol, 1, 2, 3, 4, 5. That is pentanol, pentanol. And now we have a big jump in the boiling point and the melting point. And why is that? Because this does hydrogen bonding. And hydrogen bonding is a stronger intermolecular force than van der Waals. Okay, so they're just showing you that if you have the same number of carbons, so these are constitutional isomers, right? They have the same molecular formula, but different connectivity. So can you name those? So this would be 1, 2, 3. It would be 2,2-dimethyl propane, and it has a molecular formula of C 1, 2, 3, 4, 5, hydrogen 3, 6, 9, 12, 12. Here, this is 1, 2, 3, 4. This is 2-methyl butane. Has a molecular formula of C 5, 8, 3, 6, 9, 10, 11, 12. So you see that they have the same molecular formula but different connectivity. So these are constitutional isomers, and these constitutional isomers have different names, they're different compounds, and even though they're both van der Waals, they're going to have different boiling points and melting points. And here, because they have the same number of carbons and they have more branching, they're going to have a lower melting point, but a higher melting point, but a lower boiling point. This is kind of an anomaly that you see with regards to boiling points and melting points. Alkanes are more soluble in organic solvents. Alkanes are insoluble in water. We talked about that. Okay, what is the name of the compound below? So let's draw this compound. All right, so you got to find your longest chain. I'm going to number it. So 1, 2, 3, did you get octane? And are you going to number it from left to right or right to left? That puts it at 3. So 1, 2, 3, 4, 5, 6, 7, 8. So you want to go from left to right because that gives a substituent at 3, whereas this one would be 1, 2, 3, 4, 5. So 3 is less than 5. Now here we have 3-methyl and a 3-methyl. And here we have a 4-isopropyl. And so when you combine these, the 3,3, it should be 3,3-dimethyl. See there, 3,3-dimethyl, and then 4-isopropyl. And you choose there the iso, I comes before M. So there is your name. Okay, let's try another one. This one's a cyclo compound. And you see that you have a cyclohexane. So there's a cyclohexane. These are not cyclo, okay? There's no cyclo in the words. So this is definitely a cyclohexane. And here, I don't care whether you do alphabetical order or not. I'd probably just go 1, 2, 3, 4, 5, 6. And I would do 1-isopropyl, 3-methyl. Okay, so conformations of acyclic alkanes. So alkanes can rotate. Now we're talking about conformations. Remember, conformations are at room temperature, these compounds are constantly rotating around these bonds. They're almost like those windmills that you see for energy out in a big open field if you drive across the United States. And so if you have something different, like here, this is an oxygen, and your eyeball is looking here at this conformation, at this point, you'll see if you had to draw it, you would see that the oxygen's there, and you have a hydrogen there and a hydrogen there. The way you do the back carbon here, this black carbon, back carbon, if you're looking, you would draw it like back like that. And then, of course, you would see that, okay, this has a hydrogen there, this has a hydrogen there, this has a hydrogen there. And so this is a Newman projection. Okay, so then it can rotate. So here, this is staying the same. You see the back carbon stays the same. So in that case, you're still looking, okay, your eyeball is still looking down this carbon, and the back carbon stayed the same. So you see how I draw the back carbon the same. The back carbon is this circle here, and then the front carbon now is showing you that these are lined up. So this red carbon, the red oxygen's here, and so when these rotate, they're constantly rotating. That's what you're capturing, this Newman projection. This is called a staggered. I'm not sure if I spelled that right, if it's an A-R-E-D. You can look at it. This is called an eclipse. And you're going to find that these have different energies. Now, conformations are just kind of like you're sitting. If you lay down, you're still you, but you're in a different conformation. And that's what's happening with this free rotation around this single bond. Now, which one we have different energies. You know, if you lay down versus sit or stand, those are different energies. Laying down is the lowest energy, right? That's the lowest energy conformation that you experience. Well, you're going to find that staggered with all of these atoms far apart from each other are going to have a lower energy. And lower energy is preferred. Eclipsed, these are going to have some static energy. And that's what we're showing you here. The eclipse formation is here, where this one here is directly in front of here. These are here, and then these are directly eclipsed from each other, and your eyeball is looking here at this carbon. So there's that, and then if you have the blue carbon in the back, this is how you would draw your eclipsed in your Newman projection. But if you rotate that, you get a staggered, so it's E-R-E-D. And so if your eyeball looks through there, then how do you capture that? Well, if you make these your hydrogens coming off of your front carbon, and then you make that your back carbon, that's the circle, the back carbon, you see that that is your staggered conformation. And the staggered conformation is going to be your lower energy conformation. And this is about the dihedral angle. So the dihedral angle here is 60. Sometimes you'll see the dihedral angle written that way. This is 0. So once again, let's look at the Newman projection. And then we make that back carbon the blue. And I make all the hydrogens for that back carbon in blue. Okay, so this is how we capture the eclipse. The dihedral angle is the angle between these two. And they're saying that's 0 degrees between these two. So the dihedral angle on this one, notice I connect the dots here. I follow the lines because sometimes it can get confusing of what's connected to what. So here, the back carbon is here. Now your dihedral angle is between these two, the front carbon substituents and the back carbon, and that dihedral angle is going to be 60 degrees. And that's where you have a staggered conformation. So when you're drawing these, you're going to either draw, you can just get used to drawing like this. You either have the eclipsed, it's almost like a Mercedes sign. Okay, that's eclipsed. This is the framework, or staggered. Okay, and then you can go and put whatever the substituents are on here. This is always going to be the staggered conformation. You see how the dihedral angles are 60. This is always going to be the eclipse where they're kind of close together. And you notice that these lines in the back connect to that back circle. Okay, that's important. Where the ones in the front is going to connect to that front. And that's eclipsed. Here you have the front, and then you have the ones in the back, and they connect to the back carbon, which is the back circle. Do you see the difference between a staggered conformation and eclipse framework? And then whatever it is you can put on here based on whatever molecule you're given. Okay, so this is Newman projection, and they're showing you that the front carbon is the dot in the middle, and the back carbon that you see with your eyeball is this circle. And you have a nice POGL, I think 5A, that works through these. So the first thing you want to draw, this is staggered, right? This is your lowest energy conformation because the dihedral angles on that back are going to be the furthest away. So these are bonds in the back, and these are bonds in the front because they're connected to that center. And this is going to be the staggered conformation. So they're showing you this is ethane, and you need to be able to look at this right here and be able to draw ethane. Okay, you need to be able to recognize, you need to convert names and structures. Like I said, the POGL is good for that. Your eyeball is looking down this carbon here. That's your front carbon, and it has hydrogens on it. And then your back carbon is this circle here. And so you can see that you have hydrogens here, just like you have hydrogens there. And then you have hydrogens on the back, just like you have hydrogens on the back. Okay, like I said, this is the staggered conformation, and this is the eclipse conformation. So this is going to be your higher energy. And this is all conformations. They're rotating around this single bond. And when these hydrogens, it's really, I don't know what that was about. Okay. Anyway, there's staggered versus eclipsed. Okay, these are conformations of ethane. So this is not a big deal. These rotate at room temperature, and because these hydrogens are really small and they don't take up a whole lot of space when they rotate, it's not a big deal to go from the eclipse to staggered and staggered to eclipse. And keep in mind, you can't get to another staggered conformation without going through the eclipse. So you're constantly going around this, and it's not that big of a deal to go when you just have hydrogens there. Okay, but and so that's what they're showing you. Like, even though these are the clips and they're higher energy, so this is increasing energy, so they're higher energy, and to go through these different rotations. And these are lower energy, you see, lower energy, these valleys here are the staggered conformations. And they go from this staggered, where the red oxygen would be here, to here. It has to go through this eclipse. And that's not a big deal because they're hydrogens. Now to do this, to go between staggered and eclipse, this is called torsional energy. Like, so touch your toes, rotate your body. That's torsional. You know, it's got a torque. Torsional strain increases when you have to go through those eclipsing interactions. Now, what if these are not hydrogens? What if they're big methyl groups? That's when torsional energy is a big deal. The energy difference between staggered and eclipse conformation when you're just dealing with CH is about 3 kilocalories. Okay, so looks like we don't have the structures here, so I will put these on here. This is trying to make it look nice. This is A, and this is B. That's not really that great. Let's do this. So we'll make it without a doubt. Okay, so which framework represents a dihedral angle of 180 degrees? Well, that would be B, right? B is the staggered. This would be eclipse, so that would be closer to 0. So I would choose B. Okay, so we've been talking about ethane, but now we're going to start adding a methyl group. And so now if we have a methyl group, can you see that this is this carbon here? Because it has hydrogens. And then your back carbon is this circle here, and now we have a methyl group. And then we have 2 hydrogens here. Now, when you rotate that, you see if you made the models here, you would see that the methyl's at the top. When you rotate that, and you go through an eclipsed, and in this case, the front carbon is rotated. Now we have 0-degree dihedral angle here. Here, between the two, is 180. Now, hydrogen is interacting with CH3. This is still not that big of a deal for the eclipse, but what if your hydrogen became a CH3 itself? And that's what we're going to look at when we see butane. And so that's what butane is, and we start really seeing more of a difference between the staggered and eclipsed. So here, now we have butane, and so our eyeball is looking down this carbon here. That's your front carbon, and your back carbon is here. And so what's here is you have the rest of these are hydrogens. So yeah, you got hydrogens there, you got hydrogens there. Okay, so these are hydrogens. Hydrogens aren't that big of a deal because they don't take up a lot of space when they're rotating. But these methyl groups, this is staggered and it's anti. What is anti? That means these big groups, the methyl, are 180 degrees from each other. You see they're 180 dihedral angle. So that means staggered is anti. You can have staggered gauche, and that means there's still an anti. It's still a staggered framework, but now these methyls are close to each other, and now they're 60 degrees, the dihedral angle of the big groups, and that's gauche, G-A-U-C-H-E. But in order to rotate from this staggered anti, which is the lowest energy, this is preferred, it has to go through this eclipsed. Okay, and then it goes to staggered gauche. So these are 60 degrees. And then it goes to eclipsed, which is higher energy. Actually, it goes here first. this is probably your highest energy, right? Because it's eclipsed, but it's the bigger groups that are eclipsed. And then it goes through Gauss, and then it goes through eclipse. So your lowest energy is going to be this anti-staggered, and then your highest energy is going to be this eclipsed. And so a lot of times what you need to be able to do is draw an energy diagram. And so they're showing you that the anti-conformation with these methyl groups are the lowest in energy when they're 180 degrees apart in the dihedral angle. This is the highest energy, and you have these Gauss is still staggered. So it's still staggered, but they're showing you this is higher in energy, but it's not as high energy as the eclipse. And both of these, whether Gauss or anti, staggered is always, and whenever anybody in science says always, write that down, is always lower in energy compared to eclipse. Okay, so steric strain. Okay, so steric strain is caused when you have this eclipsing. So when your eyes are looking here and you see the eclipse with this butane, okay, so here's your butane, right? And these methyl groups are eclipsed. This is steric strain. Oh. And so the energy diagram can look like this, where you see that these 180 anti are going to be your lowest. And here it is again. And then your highest is going to be this number 4, where you have both methyl groups eclipsed. And then still these are still pretty high energy, these eclipsed. These are the eclipse framework. This is called total eclipse. So this is just eclipse. This is total eclipse. These are anti. And then these are right here. This lower energy is the Gauss. You see, sometimes you'll see it marked like that with this. This is the Gauss interaction. This is showing you actual numbers for eclipsing energies. And this is for rotation, because you get free rotation. If hydrogens eclipse each other, this is and you can look at your slides. I think some of them didn't transfer energy, kilojoules per mole. This is kilocalorie, so we'll just do kilojoules. If a CH3 eclipse, that's going to be 6. Now what if you have a CH3 eclipse? 11. So it gets to the point where sometimes these energy differences are so high that you're not going to see that free rotation, because it's not going to go through this eclipsing. But this is not a serious barrier to rotation. So these butanes will rotate into these different conformations at room temperature. You can always increase the temperature and you get more free rotation. Since the lowest energy conformation has all the bonds staggered, that's why we do this zigzag. Okay, that's why we do the zigzag for the alkanes. All right, so this is the molecule, the structure you need. Now notice when I'm drawing these, this bond goes straight to this carbon. If you do not have that connecting to the carbon, you're going to lose points, because these are bonds, these are representations. Okay, so don't draw this just willy-nilly. This needs to be a defined bond that goes from this to this carbon. This goes to this carbon. Now, how do you convert a structure like a Newman into a name? Well, you want to find your longest chain. So here, you can start here as your front carbon, And then you can go, okay, well, where's our chain? We got C, H, we'll do that CH, and then we have CH3, CH3, those branches. And then let's get all the stuff coming off of here. We got a Br, and we have a CH3. And then that's connected to this back carbon. So now we got to connect this to the back carbon. I can even just do a little circle, and then you're going to have a hydrogen and a hydrogen. And you're going to have a CH2, CH2, CH3. All right, now you can do your naming where you find the longest chain. 1, 2, 3, 4, 5, 6, 7. Okay, that's 7. Heptane. You got heptane, heptane, heptane. And then 1, 2, 3, 4, 5, 6, 7. So we got 2, 3 dimethyl and 3 bromo, heptane. All right, this is getting crazy with these. We're just going to not worry about that slide. Okay, so now let's move on to angle strain in cycloalkanes. So angle strain is an increase in energy when the bond deviates from 109.5 degrees. We talked about that with cyclopropane and cyclobutane. So now we're talking about cycloalkanes. And if these slides did not convert over, you have access to them. Okay, so this is should be, these are all sp3 carbons. So they should have 109.5 degree bond angles. As you can see, this has a 90 degree, this has a 60 degree, and then large internal angles when they deviate greater than 109 is still considered angle strain. The cycloalkanes will distort their shapes to relieve the angle and torsional strain. So cyclobutane will take on this conformation, cyclopentane, cycloheptane, and cyclodecane. Now we skipped over cyclohexane because that's what we're going to focus on in the conformation. So the nice thing about cyclohexane, when it gets into this chair, you see why it's called a chair here, like the lounge chair. When it's in this chair conformation, it actually has relieved its angle strain, and they can pretty much approach 109.5 degrees. So you need to be able to draw stable, so you need to, one of the learning objectives, I can draw stable chair conformations. So here, they're just showing you that by doing the stair conformation, then your hydrogens, or whatever substituents, they're going to have this axial, these are called axial, and these are called equatorial. And you've got some Pogel exercises that help you draw these. So, but this puts all of the hydrogens staggered. So remember, they are staggered. And so that's another reason why the chair conformation is the most stable. Now, how to draw them. You need to be able to draw them. So the first thing I want you to do is you need to draw this framework. And so a lot of times you might want to do this little paper. You know, remember that paper when you were starting elementary school with the dotted lines? Well, draw yourself some of the paper and then draw, you got 6 carbons, 1, 2, 3, 4, and see how these go to that little dotted, and you got to have the slant. Okay, they got to have the slant. You have to have the slant, okay, because that's going to be important to get the slant. So you're going to find that this is parallel with this. You're going to find that this should be parallel with this. And then of course you have this parallel with this. And that makes it for a nice drawing. And then you can erase you do this in pencil, you can erase your little helper lines. You see if we can get in here. So see, and you erase your helper lines. All right, so the first thing you do, number one, is the framework. The second thing you do is you draw in all your axial. Okay, so axial is perpendicular. If you don't draw these correctly, and I can't tell, you're not going to get credit. Okay, so this is down. You see how this is down compared to this carbon is up? This one's down compared to this carbon is up. Think about the framework. So if this is down, make sure it's perpendicular, up and down. This is axial down. And then we draw this hydrogen. We go around. Axial up. This is going to be important. This is axial down. Axial up. Axial down. Axial up. And that's all your axial. And once you do that, then you can draw your equatorial. If this is down, this needs to be equatorial up. E up. Okay, see, and it's going to be parallel to that. This one is going to be equatorial down. See, that's equatorial down, and it's going to be parallel to that. This one's going to be equatorial up. This is going to be equatorial down. It's going to be parallel to this line. This is the axial down, so this has got to be equatorial up. And I want to see that you can draw each one of these. Each carbon has to have two things. And it's going to have an axial and an equatorial. One's going to be down, one's going to be up. And so the book kind of gives you some ideas on how to draw these. And then you can see that you have 3 axials below the ring, and then you'll have 3 axials above the ring. And what's important then is to draw in your equatorials. Let's see. So let's draw this structure here. Get my drawing. Okay, choose a statement that best describes the methyl group. The methyl group is axial up. The methyl group is axial down. The methyl group is equatorial up. The methyl group is equatorial down. So what I would do is I would always draw in, okay, this should be, let's draw in all our axial hydrogens. If this one's down, then you do axial down, because they're alternating. Axial up, axial down, axial up, axial down, axial up. So if this is axial down, what is this? This has to be equatorial up. Okay, so this does a ring flipping, and you need to be able to do the ring flipping. So the ring flipping, a lot of people try to cheat on this, and I can tell when they do. This carbon here now has to be up. Okay? And then when you see that, this carbon here now is down. Now the reason why that's important, let me show you. So let's put in our axial hydrogens. See, I'm going up, down, up, down, up, down. Well, what happens is that's axial up. This is equatorial down, equatorial up, equatorial down, equatorial up, equatorial down, equatorial up. Now what happens though, this hydrogen here, up stays up, down stays down, You should memorize this when you do your ring chair. And then equatorial becomes axial, and axial becomes equatorial. And this will make a difference when you don't have hydrogens. So this, if I want to draw the ring flip here, up stays up. This is axial. Equatorial becomes axial. So now this red hydrogen is axial down, and this yellow one is equatorial up. So here on that carbon, the axial up became equatorial up. Equatorial down became axial down. Let's look at this carbon here. Okay, so this carbon here, this hydrogen here is axial down, and now the red carbon with equatorial up, that becomes axial up, and the yellow hydrogen becomes equatorial down. See, down stays down, but axial becomes equatorial. Up stays up, but equatorial becomes axial. And that's what happens when you flip them. That's what it's saying here. And so you're going to have to draw that and show that you can flip those. And that's what your POGL kind of helps you with. We don't spend a lot of time in this boat conformation and these flagpoles. These are the 3 flagpoles. And if you have the models and you try to do the flip, you'll see that to go to the flip, which that's what these molecules do, they will go through this flip to different conformations, just like you saw the acyclic alkanes go through the eclipse and the staggered conformations. So, but the cycloalkane goes through the boat and the flagpole interactions, and these are higher energy. And so this is just showing you how to draw them. And so here, this is an up carbon, so you want the axial up, and that's going to be equatorial down bond. So if you wanted to draw these different substituents, then you can just kind of, I always just draw the hydrogens in, and then I erase them and draw whatever the substituent is. Now, I'd like to point out, when this becomes important is when you have disubstituted cycloalkanes. And that's where we need to focus our attention. So we'll talk about that ring flip. And they're showing you that this, you got the down and the up, and when you do their flip, the axial becomes equatorial, equatorial becomes axial, but up stays up and down stays down. And so that's this is equatorial down. And then when you ring flip this carbon now, it becomes axial, but down stays down. Now, why is this, see the equilibrium arrows? Why is this 95% more stable? You want your larger groups or your larger substituents on these rings. They need to be in the equatorial position. So if you did a model, you could see when you rotate this, it has more space to rotate. And when it rotates, it needs to be in that equatorial position. Here, the problem with this is it's going to, there's these hydrogens here, and there's a hydrogen here. It's going to hit those. These are those 1,3 flagpole hydrogens that's going to hit. And those, well, actually they call them 1,3 diaxial interactions. And these are not favored energy, not energetically favored. I think that's what they're talking about here. All right, so the methyl group is preferred to be in the equatorial position, so it doesn't have these 1,3 diaxial interactions. It's not going to hit those. And literally, when you draw these molecules, you can hear them bump. They go tick, 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 they bump. Okay, so you want to avoid that high energy interaction. And that's a steric interaction. Here, this is a tert-butyl. Tert-butyl is so highly destabilized. I mean, you're not going to find it in this very crowded axial position. So it's going to want to be equatorial. So when this bond rotates, those methyls can rotate because they're rotating as well. And they're not going to interact with these 1,3 diaxial hydrogens. So look, that's 100% confirmation. Okay, so let's draw some of these structures in and work this problem. That's A. That's B. That's C. I'll clean these up in a minute here. And that's D. Okay, so you want to find the more stable compound. Kind of fun to draw on these drawing programs. Okay, so I don't know if I made it worse. This is what you want to do. You want to say, okay, what is this? So here, this is axial down, this is axial up. And these are dimethyls. So we're talking about 1,2 dimethyl cyclohexane. Are they all 1,2? I think that they are. This is axial down. How do you know this is equatorial down? Well, this is pointing up, this carbon, and so that would be axial up. And you can draw the hydrogens in if you need. If that is in the perpendicular plane, that has to be equatorial down. This one here, that would be axial down. So this is equatorial up, this is axial up. Here, you can draw in the hydrogen to see that that's axial down. So the substituent, this methyl, would be equatorial up, and then this would be equatorial down. So here we have both axial, so this is going to be the highest energy for these substituents. This is going to be equatorial down and axial down. This is equatorial down and axial up, so these are going to be equal in energy. And then these are two equatorial positions. See, equatorial down and equatorial up. So D is going to be your lowest, most stable compound. Lowest energy is the most stable. The other thing to note here, be careful not just to draw. If you draw them like this, you're going to get points off. All right, you do that, guess what? Each one of these is a methyl, folks, okay? So if you're going to start drawing stuff, even if you do that, you need to put the hydrogen in, because if not, that is a CH3. This is a CH3. It's a dimethyl cyclohexane. So don't just get sloppy. You're going to draw a line, you better put a hydrogen in there. Otherwise, it's a methyl. Okay, so here we have, when you're dealing with cyclopropanes, they basically have a plane. So like if you have a piece of paper here, you have a top and a bottom. And so if these are on the same side. So basically this would be like methyl top. This would be a methyl up here and a methyl up here. Okay, so this is cis if they're on the same side. So if you put your hands together, like cross your hands together with your thumb, If your thumb's on the same side, that is cis. Okay, cis. If you put your hands together and you flip them, where your thumbs, if they're on the opposite side, that is trans. Okay, so these are different isomers, and these would be diastereomers. So diastereomers are, they have the same molecular formula, they have the same connectivity, but they have different orientation in space. Okay, so here we have 1,2-dimethyl cyclopentane. But that's not okay enough. This is cis and this is trans. So these are diastereomers. So here, if you were going to draw this one, this methyl is up because it's coming at you, and this methyl is below the ring, CH3, coming down below the ring. And so they're just showing you the cis and the trans. Now, going forward, when you have disubstituted like cycloalkanes, you need to, when you're doing this in a two-dimensional, you'll see the next slide. When you do this, this is a two-dimensional drawing. I expect on your POGL to do 2D and conformations of chairs because I want you to be able to do both and back and forth. So this is a trans, 1,4-dimethyl cyclohexane. This is a cis. Do you see how you add the cis and the trans to the name? These are diastereomers. That's the relationship to each other because they have the same connectivity, they have the same molecular formula. That makes them not constitutional, but trans and cis, they have different orientations in space. Now, how would you draw this in a chair? Okay, so this is 1 and 4. So if you're going to make this up, okay, and you got to make it equatorial, maybe, right? There's hydrogen. That's CH3. That's equatorial up. That's carbon number 1. So now let's go get carbon number 4. 1, 2, 3. There's carbon number 4. Now, this is up. This is down. Equatorial down. So we have down and up. See, this has to be up and this has to be down. Now, if you wanted to make this up and that down, that's okay, but they, relative to each other, these CH3s have to be up and down. Now, let's do this one. Okay, so here we have this one here. We can make that one up. There's your CH3. So it's equatorial up. And now we go to carbon number 4. And it has to be up as well. This is up, that's got to be up because they're on the same side. So this is axial up. So which one's more stable? Well, this is an axial and an equatorial. These are both equatorial, or no, yeah, equatorial, equatorial. So this one, this compound, is more stable. It has lower energy because both substituents get to be in the equatorial position. So how do you draw the disubstituted chair? Well, like I just did, I mean, you always do your axial, and then you got to look, are they down or up? Okay, so if this is this molecule here, if we were going to convert that to a two-dimensional, okay, so if this is down, CH3, and then here's on 4, 1, 2, 3, 4, and that's up, then that would be this one. So that would be a trans 1,4-dimethyl cyclohexane. So you can go through this and you can see when you flip them, down stays down, Up stays up, but axial becomes equatorial. Equatorial becomes axial. Now they're showing the different, they're not equally stable here because this is, um, both of these are in axial. This is the ring flip. These are equatorial. So the equatorial, you see the equilibrium is going to be more stable because you want your bigger groups to be in the equatorial position. And in this case, they're going to be 50-50 because when you do the ring flip, this up stays up, but this is equatorial up, and this is axial up, and this is axial up, and this becomes equatorial up. But you have one axial, one equatorial, one axial, one equatorial. So there's going to be 50-50%. Okay, let's draw these in for you. Um, let's see. A, B, C, D. Now it says what represents the most stable conformation of 1,4-dimethyl cyclohexane? Well, this is a 1,2. You see that's 1,2. This is 1, 2, 3, 4. So this is 1, 4. 1, 2, 3, 4. That's a 1, 4. That's a 1, 4. This is a 1, 2, 3. 1, 3. So now we're just going to look at these two here because we want 1,4-dimethyl cyclohexane. That's the first thing you want to do. These are constitutional isomers, all of these. Now B and C, how are they related to each other? Well, drawing your hydrogens if you can't see it. The axial. This is axial down. This is equatorial up. This is axial up. So this is equatorial down. So how would you draw B? B is the this methyl is up and this one's down. So that could be up and this could be down. So it's going to be a cis 1,4-dimethyl cyclohexane. Now let's go look at this one here. This, because this is axial down, this is equatorial up. This is axial up, that's equatorial down. So what would C be? If this is up on the 4, and then this is, they're both on the same side, up, there's up. You need to be able to go back and forth from chair to two-dimensional. I think I did that wrong, didn't I? They're both up. So up and up would have to be both wedges. So this is the trans 1,4-dimethyl cyclohexane. So these are going to be diastereomers. And which one's going to be, you can't tell by looking at these which one's going to be more stable. You have to draw the chair. And so you see that this is an up and this is an up, and this is one equatorial and this is one axial. This one is one equatorial and two equatorial. So two equatorial is going to be more stable, lower energy than one equatorial and one axial. Okay, so I will draw these two-dimensional structures. So this is A. This is B. That's C. And that's D. Which structure represents the most stable cis 1,3-dimethyl cyclohexane compound? Well, this is a 1,3. This is a 1,3. This is a 1,3, and this is a 1,4. So D is not right. And it says cis. Well, this is cis. This is trans. This is cis. So it's not trans. So now we've got to figure out which one's more stable, A or C. So I'm going to draw the chair, and then I'm going to pick one, and then I'm going to go ahead and draw it straight into the equatorial, and it doesn't matter. I mean, I can, so this is CH3 up equatorial up, and then 1, 2, 3, we'll get there, and there's your CH3, and that's equatorial up. So that is A, and then C, here we can pick any one as long as it's relative. So this is equatorial down, and then 1, 2, 3, and this will be equatorial down. So they're both down, so that's good. And they're both on, so they're both on the same side, and they're both equatorial. So it's going to be A and C. And that wraps up your lecture material for Chapter 4. Like I said, make sure you do your POGIL, and you want to do 4 and the models and work through those in 5A and 5B, and then review all your materials for your exam.